Hello, we are in module 37 of symbolic logic course, and we are discussing this first order predicate logic. What we did in the last module was to sort of get you acquainted with the basic syntax of this first order predicate logic, but now today we are going to talk about the quantifiers, which is an interesting addition in this first order predicate logic. You will see the idea has a link with the categorical logic. So, it will not be difficult for you to grasp it, except the symbolic representation of it. That is what you have to learn. And then we are going to take on the categorical propositions, and we will try to apply the quantifiers with them. And in general, we are going to learn how to use the quantifiers. Okay, so, this is what we are going to discuss in this module 37. Quantifiers, the name itself should tell you what they are, and why we are introducing them will become clearer as we start the operation with them. But first note that the quantifiers are legitimate terms or expressions in first order predicate logic, which talks about how many, the quantity of the individuals that you want to refer to. Okay? Quantity. Are you referring to all of them? Are you referring to just one of them? Are you referring to just a majority of them? And so on and so forth. These are all quantity terms that we have learned in categorical logic also. The job of covering that quantity is by the quantifiers. Note that they speak about how many, the quantity of individuals, but they do not identify which individuals. So, they will not demarcate, they are not like names which will tell you these, this are included in this. Rather, they will simply talk about how many of the individuals you want to refer to in your proposition. This is when we use quantifiers. Symbols, well, we are coming there. Now, quantifier symbols are composed of many different components. First of all, notice we have borrowed from Aristotle the thought about universal. The quantity, when it is universal, it refers to all or every. When that happens, notice the symbol is inverted A, inverted as in upside down A, which looks like this. Take a look. It looks like A, but only inverted, upside down. That stands for the universal quantity. Get it? Now, there is also the what categorical logic talked about was particular. Whenever you wanted to refer to some, at least one, you called it the particular. Here, please note, there is a lot of theoretical reason behind that, but in first order predicate logic we will call it existential. Existential, as in you are claiming that there exist such things. Okay? In universal, there is no claim about existence. Existence as in things that are actually occupying space in your world. But whenever you are talking about the sum, there is at least one. There is a claim of existence attached to it. Notice this is the reason why it is symbolized with inverted E. The E refers to existence. Inverted E. So, it looks like this. Get it? This is inverted A for universal. This is inverted E for what used to be called the particular, but please now note, in that particular, with first order predicate logic, there is a default existence claim. So, whenever you say sum, it will be read as this inverted E reads as there exists at least one. Okay? So, this reading is something that you need to remind yourself again and again, that there is a default existence claim with the sum from now on, and it is captured by this inverted E. Now, together with these symbols, we are going to require individual variables. The quantifier symbols work with individual variables, not with constants. With constants, you never will ask how many, but with the variables, which is unspecified, with them you can ask how many of those, right. And so, individual variables are sort of, they come along with the quantifier, and they form the part, essential part of the quantifier symbols, and there will be also parentheses or brackets. So, for example, this is the complete look of the quantifier symbol. Here is the parenthesis, and here is your universal quantifier upside down A, followed by y, which is a variable. This whole thing is the universal quantifier. Get it? Or take a look into this. This is, the whole thing is your existential quantifier. The whole thing, starting with the bracket, the closing parenthesis. Here is the inverted E followed by a variable x. So, x, y, z, anything you want to pick, but it will be preceded by the quantifier expression itself, but the whole thing is the quantifier symbol. Did you understand? Now, for this, for example, will read as for all y or for every y, and so on. You can put here also x, no problem about that, but all I am saying is that the quantifier expression must contain variable, individual variable, and that individual variable could be x, y, z, any of your choice, but the reading is for all y or for every y, such that. So, we will show you how one after the quantifier what comes, etc. This is, on the other hand, the existential quantifier, which reads as there exists at least one x such that, etc. Notice there exists at least one x, which is not the case in terms of for all y. You are not saying for existing y's. We are not talking about all existing y's, but for all y's such that. But whenever you are using the existential quantifier, there is a default existence claim attached to that, and keep that in mind. Now, we are going to, if we have understood this universal quantifier and the existential quantifier, now what we will do is to apply them to represent the four basic type categorical propositions in our first order predicate logic. So, you remember AEIO, right? So, we are going to simply take them and symbolize them in our first order predicate logic. That is the first thing to do. Notice that the universals are going to be read as conditionals. Conditionals means if then statement. They are rather weakly put. Remember, there is no existence claim, and there is also the hypothetical or the conditionality attached to them. They are to be read as conditionals. How? Let me show you. For example, let us take all logicians are smart as an example of an arbitrary A proposition. All logicians are smart. Can you see the properties that are being predicated? Being a logician, being smart. Can you see that? Now, what the reading of the predicate logic is different, isn't it? But we will show you that. But first notice that the two properties are to be identified. So, being a logician, let us see Lx, x is a logician. Being smart, x is smart, is represented by Sx. How are we going to read the all logicians are smart? In first order predicate logic, we are going to read them, it is like this. This is how, as a conditional. First of all, this all, we need the quantity is specified, it is universal. So, we are going to use the universal quantifier for all x, or if you want for all y, no problem. For all x, here comes the reading that you are going to train yourself in. If X is a logician, then X is smart. If X is a logician, then X is smart. This is what all logicians are smart will mean. For every X in your domain, if that X happens to be a logician, then that X is smart. Note, there is no claim that there is such an X, it exists or not, there is no such claim. Moreover, this is just left as a conditional. If this property belongs or predicated to X, then this property also gets predicated to X. That is the way the logicians would keep it. And again, we cannot go into great details there, but there is a very big theoretical debate about this, and George Boole sort of intervened and provided a solution to give this kind of reading to the universals and so on. That is not the debate that we are going to cover here, but I am telling you that the outcome is that universals are going to be read as this kind of weak conditionals, if then statements. So, translated now, we are going to translate this. For all X becomes this universal quantifier, and this part is now going to be translated. How? If X is a logician, then X is smart. How am I going to write that? Well, like this, like this. So, Lx horseshoe Sx. Remember that I said that all the truth functional connectives, truth functional compounds are still very much part of our vocabulary, of our syntax. So, this is the translation for all logicians are smart. Okay. Here comes, first comes the quantifier, then followed by the whole sentence. All right. Now, why we need the brackets, we will try to explain to you in the next module when we talk about the scope of a quantifier. But right now, take it in that this is the translation in first order predicate logic of all logicians are smart. I have taught you two things. One, that this is a categorical proposition, but we can capture it in our first order predicate logic. Second, I said all universals are going to be read as a conditional. So, remember this. Same thing applies to your E, where no logicians are smart is taken as a random example. Fine. Once more, same properties, being a logician and being smart, these are two properties, but this time we have a no. Now, no refers to what? Universal quantity, right? We have established that in our during our categorical logic module. So, no, where we need to start again with the universal quantifier. So, our first paraphrase, before we even go into the symbolization, make it a habit to paraphrase in this quasi sort of English. So, this is our reading of this sentence first of all. So, for all X, that stands for your no, but you are saying no is a negative. Where is the negative? We are coming there. First of all, what is the quantity that you want to give it? That is universal quantity. Therefore, we need to start it like this. For all X, if X is a logician, once more, if X is a logician. So, it is not guaranteed that X is a logician, but if it has this property of being a logician, then what? Then according to this sentence, X is not smart, and that is true about every X in your domain. Get it? So, once more, for all X, if X is a logician, then X is not smart. And this translation is again once more, this is for all X, and here comes this. Now, how to translate that? Well, like so. X is not smart, the tilde appears here. Exactly as we have said it. If X is a logician, then X is not smart, preceded by the for all X. That is your universal quantifier. Okay. So, this is my E proposition. All right. Here comes the other two. Now, the other two means I and O. The I and O, which we earlier called the particulars, we are now calling them existentials. Remember, existentials, I have said, carry a default existence claim. So, whenever you are using them, you are claiming that in your domain there is exist at least one entity to corresponding whatever you are claiming. Remember that. So, these are strong assertions, stronger than your universals, because with them there is an attached default existence claims. So, let us see how we read them as. Some logicians are smart. Some logicians are smart. How am I going to do that? Well, this sum, which quantity do you want to attach to that? The existential quantity. The moment you do that, the reading is going to look sort of different. You are going to use there exist at least one x for sum. What kind of x is that? Such that x is a logician and x is smart. Now, why did we not say if x is a logician then x is smart? Okay. First of all, as I said, look at this, that you are already claiming that there is such an x in your domain, not if x is there or not, right. So, in your Venn diagram also, when we plotted I and O, you may remember we used an x to indicate a populated region, non-empty region, and the whole logic behind that was this modern logic insight that the particulars are existentials. All right. If you compare that with your Venn diagram representation of A and E, you will find that all we have said which areas are empty in them. We have shaded those areas, right. Go back and you take a look, but the unshaded areas, we have not made any comment about that. Unshaded does not necessarily means populated. Wherever you mean populated, you have to use existential and you need to put the x. Do you understand the Venn diagrams better now? Go back and revisit your AEIO Venn diagram representations, and you will see in case of the universals we never claimed that the unshaded areas are populated, whereas in the I and O, the particulars, we have put the sign of being populated by at least one entity, and that is because we believe in this, that existentials are stronger assertions. So, where you are saying some logicians are smart, there is an existent entity who is both logician and is smart. And then the translation looks like this. This is for there exists at least one x such that x is logician and is smart, will look like this. And this dot makes a heaven and hell difference in the assertion. This is much more direct and more powerful assertion. There is such an x and that x has this both of these properties. Get it? So, remember, this is what it the I gets the treatment as. Similarly, for O, some logicians are not smart, that is going to be read as there exists at least one x such that x is a logician and x is not smart. There is one such person. So, here is the translation for that. This is for there exists at least one x, and this is for x is a logician and x is not smart. Get it? Schematically speaking, the AEO IO representation is going to look like this, where you have phi and psi as any two properties. We are using the Greek symbols phi and psi to represent any two properties of your choice. Then the A schematic form would be like so. It is a conditional with the universal quantifier attached to it. The E would look like this with the tilde attached to the consequent of this, right, and we have shown this earlier. And I is going to have this kind of a form where it is with the existential quantifier and with a dot, it is a conjunction, and O is going to look like this, where there is going to be a tilde or a negation sign at the last conjunct. Okay. This is the schematic representation of all A, E, I, O propositions in our first order predicate logic. Right. I do not need to tell you this, but still for the sake of reminder that variables are the ones that will go with the quantifiers. Constants do not require quantifiers, because constants are like individual things. You do not ask how many of those, how many of you are there, there is only one, right. So, there is no need to even raise the question about how many, but variables, they deserve this kind of questions. Also, from square proposition, we are going to represent the contradiction in this way, that remember the A, O and E, I, they were contradictories. So, we can represent them like this now, that A is equivalent to negation of O. Is that correct or no? The contradiction holds. A is equivalent to negation of O. Similarly, O is equivalent to negation of A, correct? This is E. E is equivalent to negation of I, correct, because they are the contradict, and I is equivalent to negation of E. Did you see that? So, we have kept everything that we wanted to from Aristotelian logic, and still we have more coming in. But this was how to show that the categorical logic is also carried with this. The truth functional also will be there, but I will show you slowly. Now, let us talk about how to use the quantifiers a little bit. See, if we give you this kind of properties, Bx, x is a book, Ix, x is interesting, Ex, x is expensive, Gx, x is good, Rx, x is boring, and K, that is a constant, stands for a book called The Keepers. Fine. Here is the sentence: some books are expensive but not interesting. Right? How am I going to read that? How am I going to translate that? And does this sentence require any quantifier or not? That is the first thing. The properties are all here. We can see it from the key also. The quantity term that is given is sum. So, you know which quantifier to use, namely the existential quantifier. That much is sure. Okay. We are going to read it now like the predicate logic wants us to. So, how am I going to read that? This means there exists at least one x or one y or one z, any variable of your choice. So, there exists at least one y, let's say that I have chosen y, such that now we are going to assign to that, that is the thing in your domain, that is the individual thing in your domain, unspecified, but it is an individual which has what? Certain properties, such that y is a book, such that y is expensive, such that y is not interesting. Get it? So, this is the property. Now, once more, you do not be tempted to say if y is a book. Remember, you are dealing with existent individuals. There is no wishy-washy conditionality about it anymore. It has to be a strong assertion. So, existential quantifier means that it has to be a non-conditional assertion, sort of, remember that. So, reading, and I insist upon that, that before translation always go through this kind of paraphrase, because you are beginners and you need to see this sentence in the lens, with the lens of predication. So, there exists at least one y such that y is a book and y is expensive, but y is not interesting. Now comes the symbolization, and that should be very easy. There exists at least one y such that y is a book, right, and x is, sorry, this should be y. So, y is expensive and y is not interesting. Okay. So, this is where our translation will take us to, and we have learned to use the quantifier also. Quantifier variable, it rules over the variables. You are talking about certain individuals in your domain, unspecified, which are books and which has certain properties. Let us try another one. No expensive things are good. No reference to books. No expensive things are good. How are we going to translate that? So, let us take a look. First of all, no means universal quantity, right. So, you are going to use the universal quantifier. So, you need some for all y, for all x, and so on. So, suppose you say that for all x, then if x is expensive, x is not good. X is what? X is anything in your domain. That is what it says, no expensive things are good. So, once this is done, the translation will become easier. For all x, if x is expensive, x is not good. Why this if then? I have given you the answer already. Whenever you are dealing with universals, remember to treat them as a conditional. So, if x is expensive, then x is not good. Where does it show not good? The tilde attaches here. That is a classic E proposition. I have shown you the schematic form of the E also. So, you can see that is what we have followed. Let us do the third one. No good books are boring, but the keepers is not good. Okay. So, no good books are boring, but the keepers is not good. And you can do this paraphrase first. No good books are boring, but there is a but, and then the keepers is not good. So, the translation now looks like this. For all x, if z is a book, this is a z. So, for all z, if z is a book and z is good, then z is not boring. Get it? Rx, that is for x is boring. But the keepers, that is a constant, that is a name of a book. So, the keepers is not good. Do you see that? So, what you have here is the capturing the whole thing. Why did we leave the k out? Why did we have the dot outside? Again, I will try to answer these questions in our next module when we talk about the scope of a quantifier. But right now, we are understanding how to use the quantifier. Now, remember, the quantifier requires the variables to operate on, not a constant. Okay? That is my first answer to your question. So, there is few more to go along with. These are, you saw some kind of predicates, but now let us say we have this kind of two place predicate where x is a person and kxy, x knows y, and you have Mahatma Gandhi. So, you have m, that is a small m, and small s for Sachin. Now, let us see, everyone knows Mahatma Gandhi, very good. So, everyone, that certainly is for all x, if x is a person, then x knows Mahatma Gandhi. That is our translation. So, then the translation looks like this. For all x, if x is a person, then x knows Mahatma Gandhi. Look at this ordered interpol. So, there is a certain sequence, who knows whom. Compare that with Sachin knows everyone. Sachin knows everyone. You can't say there exists at least one S such that S is Sachin, because Sachin is individual already. You do not need a quantifier to rule over Sachin. On the other hand, this everyone, you need a quantifier. So, how do we read that? The reading is, if you want to start here, the quantifier will show up. For all x, if x is a person, Sachin knows that person. Okay, that is what we mean by Sachin knows everyone. And the translation is like this. For all x, if x is a person, then ksx. Okay. This is how we will move from here, and this is the last one, very last one for this module, that suppose we have Sachin reads some of the books by Mahatma Gandhi. Sachin again not quantifiable, but the books are. Mahatma Gandhi is also not quantifiable, but the books are. So, some books are such that they are read by Sachin, and some books are such that they are authored by Mahatma Gandhi. So, this is how we will read it. There is at least one y such that it is a book, it is read by Sachin and is authored by Mahatma Gandhi, and our translation will look like so. Okay. With that, I am going to close this module. We will try to do more in the next module in this, but so far we have covered the quantifiers and I have shown you how to use them. Thank you.